Research on Collagen and Bioglass Scaffolds by Jonathan Belanger, Yu Sun, Babette Smith, and Lilith Smith. The topic of this presentation is collagen and bioglass scaffolds research being done at the Materials Engineering Department of McGill University. The research involves combining collagen and bioglass into scaffolds that can then be used in the human body to promote bone growth. It is being performed by Professor Shawan Nazat and his research team of undergraduate and graduate students. The team is composed of 3 different engineering disciplines: materials engineering, bioengineering, and ceramic engineering. The interaction of these engineering disciplines is vital to the success of this project. Each discipline brings a separate area of expertise in order to create a unified whole. If this research proves successful, it will be of a great advantage to society. One major outcome will be the benefit on medical systems. This will be achieved by lifting the weight on the medical systems when it comes to treating bone diseases, such as osteoporosis, and healing broken bones. In our overview of this research, we will address how bioengineering, material engineering, and ceramic engineering contribute to the project. We will also highlight how this research positively impacts society. Materials engineering has been around since the start of human history. Creating tools out of sturdy materials was one of man's first challenges. Materials engineering looks at the properties of materials such as conductivity and solubility, and can design, create, and test new materials for various applications. A material may be chosen for its ability to resist oxidation, its inability to conduct electricity, or its strength-to-weight ratio. The properties that are looked at include chemical, physical, and electrical. Another aspect material engineers look at is how the processing of a material affects its properties. Everything from computer chips to aircraft wings to swords were created with some aspect of materials engineering. Without materials engineering, many innovations in other fields could not be possible. Collagen is the most prevalent protein in mammals and has many properties that make it handy in biomedical applications, like its biocompatibility. However, it lacks mechanical properties such as strength and stiffness, which is a problem in bone tissue engineering. In the research being done by Professor Shawan Nazat alongside undergraduate and graduate students at McGill, bioglass is being developed to increase the mechanical properties of collagen, such as its strength and stiffness. The material used can't interfere with the properties of collagen that are needed for bone tissue growth. A composite material is created through an extensive process that requires material engineers to investigate how the properties of the material used are affected during each step of the process. Bioengineering is the application of concepts and methods of biology to solve real-world problems related to life sciences or the application thereof, using engineering's own analytical and synthetic methodologies. Unlike traditional engineering, bioengineering as a new engineering field uses mostly molecular biology to study and advance applications of organisms and to create biotechnology. Nowadays, rather than study large-scale efforts, bioengineering takes a view at the molecular and cellular level and can be applied in energy and the environment as well as healthcare. Also, though people always want to distinguish between bioengineering and biomedical engineering, the differences between them are not enormous, in which biomedical engineers are specifically focused on applying biological and other sciences towards medical innovations, whereas biological engineers are focused primarily on applying engineering principles to biology, but not necessarily for medical uses. In this project, bioengineers take care of the biological interactions between the collagen or bioglass and the human body. Bioengineers also take care of the differences between bioactive and bioinert materials. Bioactive means the chemical bond will happen between the human body and the material, which will securely attach the scaffolds to the section of the bone. This will eventually allow the body to use the benefits of the material, therefore speeding up the healing process, whereas bioinert materials will add nothing to the healing process. Also, one of their jobs is to make sure the artificial tissues will not react harmfully with the human body. To test tissues, just like other medical instruments, the scaffolds will be tested on animals. But now engineers are testing the scaffolds in simulated body fluid, which has similar chemical composition to the human body, and will mimic what type of interactions will happen to the scaffolds. Ceramics engineering was formed as a specialized branch of materials engineering, and is comprised of engineers who work with ceramics. Ceramics are non-metallic inorganic materials that are processed at high temperatures or by using precipitation reactions from high-purity chemical solutions. These materials are normally crystalline in nature and are formed between metallic and non-metallic elements. Some examples of ceramics are porcelain, glass, and cement. Ceramics are very versatile and useful materials, so can be used in a wide range of research and industries, such as mining, food and chemical industries, and biomedical engineering. Within biomedical engineering, ceramics engineers have been involved in many projects, such as the development of artificial burn and biodegradable splints. The main involvement of ceramic engineers in this project is in the development of bioglass. This is vital to the project because ceramic engineers can understand and control the degradation rate of the bioglass in the scaffold. They do this by modifying the addition in the glass-forming network. In this case, the glass-forming oxide is silicon. Controlling the degradation rate is important because when the glass dissolves, it releases ions, which have an effect on the healing process in the body. In other similar research on collagen bioglass scaffolds, ceramic engineers have altered the composition of the glass and used a different network-forming oxide. This is done to control the dissolution of the glass and the ions that are released, so a ceramic engineer can specifically target the glass for certain applications. The glass will form HCA, hydroxycarbonated apatite, which is the building block for burn. This targeting means that the collagen bioglass scaffolds can be moved from hard to soft tissue repairs depending on the type of glass and the composition used. This research is furthering medicine and will advance the technology that medical professionals use. It will also help to alleviate the pressure on the medical system for continued rehabilitation by making the recovery time shorter and more simple to manage. For example, osteoporosis is the cause of more than 8.9 million fractures annually. This means that there is an osteoporotic fracture every 3 seconds. Women are more likely to suffer from osteoporosis, with an estimated 200 million women affected worldwide. This simple example demonstrates how severely burn injuries affect worldwide health. The collagen bioglass scaffolds will speed up the healing process of the burn and will strengthen the new burn that has grown. This will greatly relieve pressure on the medical system, but will also aid in relieving pain for those suffering from burn injuries. This research being done at McGill is a great demonstration of how different disciplines of engineering can work together to benefit society. In our project, we have shown how material, bioengineering, and ceramic engineers can each bring something to a project to work towards a final product. The material and ceramic engineers develop suitable bioglass material, and the bioengineers make sure the bioglass will interact well with the human body. The final result will be of a huge benefit to society and also to the medical system. This research would not be possible if it were just engineers from one discipline working on it, because they wouldn't have a wide enough range of expertise. Our aim has been to show how having multiple engineering disciplines work together can create extraordinary results, and we hope we have achieved it. Thank you for listening.